Ever wonder why some AI models are super powerful, but also super slow? Or why smaller models sometimes struggle to keep up? Scientists are tackling this with a technique called knowledge distillation, a way to transfer the brain power of big AI models to leaner, faster versions. But here's the twist, even the best methods have blind spots. Today, we're diving into a breakthrough approach, inspired by something you might find at the gym. Knowledge distillation works like this. A massive, complex AI model, think of it as a super smart teacher, passes its expertise to a smaller, faster model, the student. This lets the student mimic the teacher's skills without the computational heavy lifting. But there's a problem. When training the student, it often forgets earlier lessons or gets stuck in repetitive patterns. It's like a gym newbie trying to lift weights way too heavy too fast. Things go sideways. That's where a new framework called POCL, Progressive Overload-Based Curriculum Learning, comes in. The name sounds technical, but the concept is simple. Train the student model like an athlete, starting with easy tasks and gradually increasing difficulty. It's like a personal trainer designing a workout plan, not throwing you into a marathon on day one. Here is how POCL works. First, the system rates the difficulty of training data, sorting it from simple to complex. Then it introduces this data in stages, like a coach increasing weights over time. Early on, the student tackles easy examples. Think of it as learning basic math before calculus. As it gets better, the challenges get harder. This gradual approach prevents the student from getting overwhelmed or forgetting earlier lessons. Imagine teaching a kid to ride a bike. You'd start with training wheels, then let them practice on flat ground, then tackle hills. If you toss them onto a mountain bike right away, they'd crash. POCL does the same for AI models, ensuring they build skills step by step. And it's not just theory. Researchers tested POCL with models like GPT-2 and found it boosts performance across the board. The student models became faster, more accurate, and less prone to errors, without needing extra computing power. Just a smart way to organize training data. But let's get technical. The study also explored how to structure the training data itself. They tested two approaches, E2H easy to hard and H2E hard to easy. The results: E2H consistently outperformed H2E, with improvements of up to 29.61% on benchmarks like DollyEval and VicunaEval. It's like a student mastering basics before tackling complex problems. But here's the kicker, the teacher's strategy also mattered. Some teachers curated data during training, adjusting lessons on the fly, like a tutor adapting to a student's progress. Others pre-selected data first, like preparing a textbook. The best results came from combining smart sample ranking with dynamic data curation. It's like giving a student the right mix of guided practice and independent challenges. Now let's talk about temperature, a value that controls how uncertain a model's predictions are. Lower temperatures make predictions more confident, while higher ones soften them. The study tested changing temperatures during training. For example, starting at 2, softer, and dropping to 1, more confident, boosted performance in some cases. But it wasn't a one-size-fits-all. Sometimes the opposite worked better. It's like adjusting the difficulty of practice problems mid-lesson to keep the student challenged but not overwhelmed. Finally, they experimented with SDF ratios, essentially how much data the student focuses on for specific tasks. Ramping up the ratio from 0 to 0.3, like gradually increasing focus on tricky questions, improved results, but dialing it back down didn't always help. It's a balancing act. Too much focus on hard tasks early on can confuse the student, while too little leaves them underprepared. What's the takeaway? The way we structure training data and tweak parameters can make or break a student model's performance. But there's still more to explore, like how these strategies work with bigger models. Future research might reveal whether larger AI students need different approaches, since they might already grasp complex concepts faster. This isn't just about making models faster, it's about making them more reliable. As AI becomes more integrated into our lives, innovations like POCL ensure smaller, efficient models can handle real-world tasks without sacrificing quality. So next time you interact with an AI, remember, behind the scenes, scientists are working hard to make sure it's not just powerful, but also smart about how it learns. Thanks for watching. If you want to see how POCL stacks up against other methods or dive deeper into the math, hit that subscribe button. Stay curious, and let's keep unraveling the mysteries of AI together.